This video, we're going to look at rational functions and we're going to look at how to simplify rational expressions. So we're going to start out with what is a rational expression. So a rational expression can be written in the form P over Q, where P and Q are both polynomials and Q is not equal to 0. So that part is extremely important. Q cannot equal to 0. So anything that's in the denominator of a rational expression cannot be equal to 0. So that starts to look specifically at the domain. So some examples of rational expressions. We've got 3 here. So we've got some polynomials, and each one of these has a polynomial in your numerator. That would be like your P. And then the denominator, that would be your Q. Again, numerator, denominator, numerator, denominator. So what exactly are we going to do with these? So first thing I want to talk about is a little bit more about that domain. So a rational expression is going to be undefined if the denominator is equal to 0. So for example, if we have this rational expression, x squared plus 2 over x minus 3, this is going to be undefined when x equals 3. Because if we look at the denominator, in our denominator we have x minus 3. If I take that and tell you, okay, well, I know that x minus 3 can never equal 0. That can never be true. Well, the time that that will happen is if x equals 3. If I plugged in 3, that gives me 0, and I can't have that. So what that's saying is that my denominator, I cannot plug in a 3. Okay, so if we looked at this one, are there any values for x for which the rational expression is undefined? So again, when you see undefined, or when we're looking at the domain of a rational expression, we're focusing on that denominator. And I want to know, when would that be equal to 0? So I'm going to take the denominator and I'm going to set it equal to 0, and then I'm going to solve. So if you don't remember how to solve this one, first thing we would do is subtract that 45 and divide that by 15, and that's how we get undefined when x is equal to negative 3. Okay, so here, if I ask you to find the domain, when you're asked to find the domain of a rational expression, what you're looking for is everything that does not make the denominator 0. So the domain are the values that do not make the denominator equal 0. So in this case, I'm looking for the 0 in the denominator. Easiest way to find the domain. Take your denominator, and we're going to say 4 cannot equal 0. Okay, well, that just looks weird, right? 4 is never going to equal 0. So what that means is there is no value that would ever make this equal to 0. So the domain of this is everything. Everything is okay. I can't plug any value into that denominator and get 0. So my domain for number 1 would be all real numbers. And so you can write that. You may see it written with this bold R. In interval notation, it would be negative infinity to positive infinity. Okay, let's look at 2. So in 2, again, we're going to take our denominator, because that's what we're focused on, and we're going to say, we want to know, when does 5 plus x, it cannot be 0. Never. So we're going to solve that. And we solve a not equal to 0 the same way we would solve it if it was equal to 0. So that means I'm going to subtract my 5 over. So x cannot equal negative 5. So what that means is that my domain can be everything except negative 5. So if I needed to write this in interval notation, okay, I'm going to have everything from negative infinity all the way to negative 5, and then I'm going to skip over negative 5 and go all the way to positive infinity. So again, this is what it would look like in interval notation. But that's just saying it's everything except for negative 5. All right, let's look at a couple more examples. So again, we're going to start out looking at our domain. And I'm going to take that domain and I'm going to say x squared minus 64 cannot be 0. And now I need to solve that. So this is a difference of squares. So I can factor that into x plus 8 and x minus 8. Well, the only way this could be 0 is if one of these is 0. So I can say that either x plus 8 not equal 0 or x minus 8 not equal to 0. Then x is not equal to negative 8 and x is not equal to positive 8. And that would be my domain. Anything is fine except for those two values, because if I plugged either one of those values into x, it's going to give me a 0 in the denominator, and that's not okay. Okay, look at this one. Again, same idea. I'm going to take this denominator. I'm going to set it not equal to 0. So x squared minus 11x plus 24 cannot equal 0. So I'm going to start by factoring this. Anytime we have a quadratic, we need to factor it. So that's going to factor into x minus 8, x minus 3, not equal to 0. And remember, factoring, I'm looking for numbers that multiply to 24 and add to negative 11. So negative 8 times negative 3 gives me positive 24, and negative 8 plus negative 3 gives me negative 11. So x minus 8 not equal to 0, and x minus 3 not equal to 0. So x cannot be 8, and x cannot be 3. So this means that any number is in my domain except for those two. So now that we understand domain, let's look at how to simplify rational expressions. So simplifying a rational expression means that we're going to write it in its lowest terms, or its simplest form. So we're going to look at this as a two-step process. First thing we want to do is completely factor. Completely factor. And we want to factor the numerator and the denominator. After we do that, the second thing we want to do is divide out any factors that are common to the numerator and the denominator. And the reason we're going to do that is that's the same thing as removing a factor of 1. Because remember, anytime you have something that's the same in your numerator and your denominator, like 2x over 2x. Dividing something by itself, that's the same thing as 1. And so let's look at some examples. We start with example 1. It says simplify the expression. I want to take this piece by piece, so I'm going to start. There's really nothing to factor here, but I can look at my 15 and my 5, okay? And I can divide out anything that's common there. Well, if I think about 15 divided by 5, well, that just leaves me with 3. And then if I look at my x's, well, I've got x to the third over x. So that means that I've got 1x I can take out, and that leaves me with just 2 on the top. So I've got 3x squared. Final answer. Okay. Number 2. I do have something I can factor here. So I'm going to try to factor before I do anything. I can't go and start crossing out x's here like I did in number 1 because of these plus signs. Only do that if you have a monomial. Remember that's, one term. So example 2, we're going to factor first. So I'm going to factor my numerator. And in my numerator, I can factor out a 7. I can also factor out an x squared. So that's my GCF. When I do that, it leaves me with 1 plus 3x. Now I'm going to factor the same thing at the bottom. I'm going to look for a GCF, and that GCF is 10. And they both have an x. That leaves me with 1 plus 3x. Now notice these are the same. So I have a common factor that I can cancel. So when I do that, I'm left with 7x squared over 10x. Well, I can continue reducing that as well because this x and this cancel because that would make that just 1x on the top. So I am just left with 7x over 10. Again, I'm going to try to factor if I can. I can't factor anything in 24, but I can factor that denominator. So we'll bring 24 down, and I can take a 3 out. That leaves me with m minus 6. So I can simplify that 24 and that 3 because I can take a 3 out, and 24 would become 8. And that's all I can really do on this one. So I've got an 8 and m minus 6. Now, I didn't have a denominator left in the first one. I did have a denominator left in the second one, but it was a 10. There was no x down there. In this one, I have a variable left in my denominator, so I need to also list out a domain restriction. And so I know that my denominator cannot equal 0. So that means that m cannot equal 6. Because if I plug a 6 in, I'm going to get 0 in my denominator. All right, let's look at a couple more. So in example 4, sometimes these can be tricky. They look really close, but they're not the same. If you notice, the 5 in the numerator is positive, but the denominator is negative. Then if you notice, this m in the numerator is negative, and the denominator is positive. So they're almost the same, except for the sign. So what we can do in situations like this is we can factor and make them the same. So I'm going to start by factoring out a -1 in my numerator. When I do that, remember factoring is like dividing. So if I divide a -1 by that 5, it's going to become a -5. And then a -1 on that m, it's going to become a plus m. Okay, I'm not going to do anything to the denominator. Just going to bring it over. Well, now if we look at them, the signs are the same. So I'm going to rearrange the order in the top so you guys can see. So I'm going to just write that m first, write the 5 second. Now I can see that they are the same. And I can cancel this and this. And the only thing I'm left with is a -1. So when you have something like this and they are the same, the only difference is the sign, they can cancel. They'll cancel to a -1. And you'll see this quite often. I'm going to highlight that so that you can kind of mark it and come back. Anytime that you have something like this and they cancel, the signs are different, but everything else is the same. They will cancel to a -1. Okay, number 5. This has already been factored for us. Is there anything we can cancel out? So if you look, there's a y minus 3 and a y minus 3. That leaves us with y plus 7 over y plus 8. And that's it. Nothing else can cancel. Now I've got a denominator that has a variable in it. So what would make that? 0, a -8. So y cannot equal -8. All right, last one. I need to factor this. So in that numerator, I'm looking for numbers that multiply to positive 36 and add to positive 13. So that's going to factor into y plus 9 and y plus 4. My denominator, I need numbers that multiply to 45 but add to 14. So that's y plus 9 and y plus 5. And so now my y plus 9s can cancel, and I'm left with y plus 4 over y plus 5. Again, since I've got a denominator that has a variable, I want to list out that restriction. So y cannot equal -5 because that's going to give me a 0 in the denominator.